Hello students, welcome to the lecture on matrices, and after the lecture we will be able to learn the following objectives. Explain the sum of matrices, explain the product and the inverse of a matrix, describe the adjoint of a matrix. Let's start with a brief introduction to the matrices. A matrix is a collection of numbers ordered by rows and columns. It is customary to enclose the elements of a matrix in parentheses, brackets or braces. A vector is a special type of matrix that has only one row called a row vector or one column called a column vector. A scalar is a matrix with only one row and one column. It is customary to denote scalars by italicized lowercase letters, example x, to denote vectors by bold lowercase letters, example x, and to denote matrices with more than one row and one column by bold uppercase letters, example x. Real and complex matrices. As in the case of vectors, the components of a matrix may be real or complex. If they are real numbers, the matrix is called real and complex. Otherwise, for the present exposition, all matrices will be real. Square matrices. The case m equals to n is important in practical applications. Such matrices are called square matrices of order n. Matrices for which m is not equal to n are called non-square. Square matrices enjoy certain properties not shared by non-square matrices, such as the symmetry and anti-symmetry conditions. Let's now take a look on the sum of the matrix. If A and B are matrices of the same size, their sum A plus B is the matrix formed by adding corresponding entries. For better understanding, let's see the example on your screen. Let us understand the matrix algebra determination. A matrix is an array of numbers. Determinant, the determinant of a matrix, is a special number that can be calculated from the matrix. It tells us things about the matrix that is useful in systems of linear equations, in calculus and more. The symbol for determinant is two vertical lines either side. Calculating the determinant. First of all, the matrix must be square, that is, have the same number of rows as columns. Then it is just a matter of basic arithmetic. For better understanding, let's have a look at the screen. Matrix multiplication. If A is an Mn matrix and B is an Np matrix, then C is an Mp matrix. We use Cij to denote the entry in row I and column j of the matrix C. Standard row times column. The standard way of describing a matrix product is to say that Cij equals the dot product of row I of matrix A and column j of matrix B. For better understanding, let's see the formula on your screen. Column times row. A column of A is an M1 vector and a row of B is a 1P vector. For better understanding, let's see the example on your screen. The columns of this matrix are multiples of the columns of A and the rows are multiples of the row of B. If we think of the entries in these rows as the coordinates 212 or 318 or 424, all these points lie on the same line. Similarly for the two column vectors. Inverses of matrices. If A is a square matrix, the most important question we can ask about it is whether it has an inverse A the power minus 1. If it does, then A the power minus 1A equals to I equals to AA, the power minus 1, and we say that A is invertible or non-singular. If A is singular, that is A does not have an inverse, its determinant is 0, and we can find some non-zero vector x for which Ax equals to 0. For better understanding, let's see this example on your screen. Matrix transpose. The transpose of a matrix is denoted by a prime A dash or a superscript T or T, A the power small t or A the power capital T. The first row of a matrix becomes the first column of the transpose matrix. The second row of the matrix becomes the second column of the transpose, etc. For better understanding, let's see the example on your screen. The transpose of a row vector will be a column vector and the transpose of a column vector will be a row vector. The transpose of a symmetric matrix is simply the original matrix, using the inverse matrix to solve equations. One of the most important applications of matrices is to the solution of linear simultaneous equations. For better understanding, let's see the example on your screen. Let's talk about adjoint of a matrix. In linear algebra, the adjoint matrix of a square matrix is something similar to the inverse of a square matrix. When A is invertible, the difference between the adjoint of a matrix and A the power minus 1 is just a scalar. However, the adjoint matrix can be defined for any square matrix, not necessarily invertible. Finding the adjoint matrix. Find the transpose of A, which is denoted by A the power t. The transpose is found by interchanging the rows and the columns of A. So for example, the first column of A is the first row of the transposed matrix. The second column of A is the second row of the transposed matrix, and so on. The minor of any element is found by covering up the elements in its row and column and finding the determinant of the remaining matrix. By replacing each element of AT by its minor, we can write down a matrix of minors of A, the power T. The cofactor of any element is found by taking its minor and imposing a place sign according to the rule. For better understanding, let's see the sign on your screen. The matrix of cofactors of the transpose of A is called the adjoint matrix ADJA. Now in the end, let us summarize what we have learnt in this lecture. A matrix is a collection of numbers ordered by rows and columns. It is customary to enclose the elements of a matrix in parentheses, brackets or braces. A vector is a special type of matrix that has only one row, called a row vector, or one column, called a column vector. For a 2 by 2 matrix, the determinants is add ADBC. For a 3 by 3 matrix, multiply A, determinant of the 2 by 2 matrix that is not in a rows or columns. Likewise for B and C, but remember that B has a negative sign. A scalar is a matrix with only one row and one column. A diagonal matrix, symmetric matrix where all the off-diagonal elements are 0. An identity matrix is a diagonal matrix with ones and only ones on the diagonal. The product of matrix A and column J of matrix B equals column J of matrix C. This tells us that the columns of C are combinations of columns of B. A. This tells us that the columns of C are combinations of columns of A. The product of row I of matrix A and matrix B equals row I of matrix C, so the rows of C are combination of rows of B's.